Welcome everybody to this panel discussion on MSR startups and MSR technology and economic prospects and whatever topic might arise with each one of you. We have a 2 hours session here. My name is Jan Kloosman. I work at Delft University of Technology in the field of reactor physics, and I'm coordinator of the SAMOSAFER project that runs currently in Europe. I would like to introduce you the panelists that we have today. I put them in alphabetical order here. So first is Dr. Koen Chen. He represents Thorcon, that I will explain later on. Koen Chen is the Chief Nuclear Officer in Thorcon, and he has been focusing on developing advanced nuclear reactors to provide reliable and affordable energy to the world. Before that, he was Vice President Licensing at Moltex Energy in Canada. And before that, he was director of the Reactor System Engineering Division in SINEP, Shanghai, and a distinguished professor of the Chinese Academy of Sciences. Welcome, Koen. The second panelist is David Leblanc from Terrestrial Energy. David has dedicated his career to the improvement and realization of advanced nuclear power system, in particular MSR technologies. And his work has focused on the simplification of design and reduction of R&D requirements to realize the goal of MSR. And he obtained his PhD in physics from the University of Ottawa in 1998. Welcome, David. The third panelist is Elsa Merle, professor at Grenoble Institute of Technology and LPSC since 2000. Elsa is involved in many European projects and many national projects in the field of MSR. She leads the CNRS programs dedicated to Gen 4 reactors, and she contributes, as I said, especially in the field of molten salt reactors through simulations, measurements, and also nuclear power scenario studies. Welcome, Elsa. The fourth panelist is Dr. Truls Schoenfeld. He's executive officer at Seaborg. Truls initiated his career as a particle physicist at CERN in Switzerland, the Niels Bohr Institute in Denmark, and the European Spallation Source in Sweden, and then back at DTU in Denmark. He calls himself a radical pragmatist who unintentionally became an impact entrepreneur and CEO when he co-founded Seaborg in 2014. Welcome, Truls. And then last but not least, Ian Scott. He's founder and chairman of Moltex Energy. His main career has been in the biological sciences, rising to chief scientist for Unilever and founding a drug discovery company afterwards. He was drawn into nuclear energy by the understanding that without low-cost nuclear energy, the climate crisis would not be resolved, and the belief that current nuclear technology simply cannot be achieved through cannot achieve the necessary economics. Welcome, Ian, also to this panel. So these are the 5 panelists, and we will have now 4 times 15 minutes presentation. Please tightly stick to the 15 minutes so that we have also ample time to have a discussion afterwards. And I would like to give the floor first to Koen Chen, Thorcon. Koen, are you ready?
Yes, of course. Let me just try to share my screen with you guys. So I'm supposed to be sharing my presentation window. Okay, yeah, if you can tolerate the small bar on top of the slides, I won't enter the full screen mode, because this way I can see you guys while I'm talking.
Okay.
Okay.
I think it's clearly visible, Koen, so it's okay. Please go ahead.
All right. Excellent. Thank you very much, Yang Ling, for giving me this opportunity to talk to the students and faculty members in this summer school. I'm representing Thorcon. So in Thorcon, we're thinking about energy poverty and climate change at the same time. As most of us would agree that access to energy is at the heart of the development of a country. And unfortunately, the energy generation could also produce greenhouse gas emissions. While we think in Sorkhang, we think nuclear can provide abundant energy while fighting climate change at the same time. However, the first question is how much electricity the world would need. So if you look at this slide, and on the left, it's a current trend. The bottom light blue ones are the electricity generation from 2010 to 2050. That is for the OECD countries. You can see the generation would remain flat throughout the years, while the darker blue ones are for non-OECD countries. Their generation will increase over the time all the way to 2050. But more striking is the per capita generation. And on the top, it's the per capita generation of the OECD countries. On the bottom is the per capita generation for the non-OECD countries. The gap is very obvious. And the current trend, even though the electric generation increase in the non-OECD countries will continue, but the gap will now be narrowed. So the increase of electricity in the non-OECD countries in the current trend is almost all due to the increase of population. So that means you're not increasing the living conditions of people in those countries. On the right, we have a very bold prediction that eventually the non-OECD countries will be able to catch up the OECD countries, which probably not going to happen in 2050, but most of the countries would hope that they would be better in 2050 than this year. And obviously, Indonesia is one of that countries. And Indonesia is the world's fourth most populous country with 270 million people. And however, the per capita electricity consumption is only 1/6 of Europe. And it's a very beautiful country, and I'm very much looking forward to visit that country many times, but they do need electricity. They need development. So if we take a closer look at Indonesia, again, I want to highlight those 3 lines on the left. And the bottom one is the per capita electricity generation in Indonesia and its trend. And the middle one are the non-OECD average. The top one is the OECD average. You can see the per capita generation of electricity in Indonesia not only significantly lower than the OECD countries, but it is also only half of the non-OECD countries. So obviously, the people in Indonesia want to catch up with everyone else, want to improve their livelihood. And today, Indonesia only generates 0.28 trillion kilowatt hour electricity per year, which is about half of France. But considering the population, the per capita number is very, very low. If we just follow the historic trend, by year 2050, Indonesia would need to add half of France electricity generation. But Indonesians won't be happy with that. They want at least catch up with the non-OECD average. In that case, they would need 1.25 France. And if they want to do better than the average, if they want to get more closer to the OECD countries, they would need several or a few France electricity generation. And their own government predicted that the country would need to add new capacity of 350 gigawatt by year 2050. And the question is, can they do that while keep fighting the climate change and protect their environment? And can nuclear help for them to achieve this ambition? Well, the simple answer is not with the traditional nuclear. If you look at the figure on the left, this is IEA projection of nuclear power in the world. The light blue one is their pessimistic projection, while the darker ones is their most optimistic projection. As you can see, if we're using their pessimistic projection, we're barely able to keep the nuclear power generation over the next 30 years. We're probably going to lose some and probably going to add some, but overall, it's not going to increase at all. And in their most optimistic ones, and we still see the percentage of nuclear in the total electricity generation will remain flat. And you can imagine with this type of a increase, nuclear won't be able to help Indonesia to achieve its goal. The countries like Indonesia and other non-OECD countries, they would need 75% nuclear instead of the 10 and 15% following the current trend if they're lucky. Those countries, they're not going to just need a few nuclear demonstration plants. They actually need to deploy a massive nuclear power fleet rapidly. But what things are hindering those countries? What things are hindering nuclear? Well, construction, licensing, and workforce development would be the key topics. If you read the published reports from within the nuclear industry or other observers, and those three things were frequently mentioned in those reports. And we in SORCON believe that we have a solution for those issues. So here's how we're going to build the nuclear fleet. And we can literally build a fleet because the founders of SORCON, they're from the shipbuilding industry. They have built the world's largest ships over the past several decades. And coincidentally, or intentionally, the SORCON 500 megawatt plant is about 60% size of a large oil tanker. And each of those oil tankers only cost about $90 million in the past. So if we build the nuclear power plants at ships in the shipyard, we'll be able to enjoy the low cost and rapid construction in those facilities. A shipyard, a typical modern shipyard, can build 20 gigawatt-e SORCON plants each year. Think about that. That means you can build more than 10 EPRs per year in one single shipyard. But of course, you cannot build an EPR in shipyard. You can only build SORCON power plant in shipyard. And we have a modular design that fits best with the shipyard. So the plant actually has use low enriched uranium, fluoride salt fuel. We use moderator, so it's a thermal spectrum. And as you can see on the left, the figure is really like a ship. Everything is modular, it's replaceable, and it's ready for a massive production. So the cost is really impressive. For each gigawatt E, the cost is only about $1.2 billion. And the electricity cost is about 3 cents per kilowatt hour. And how this is gonna work? So we're gonna start build the power plants in a shipyard on the left, which is a real picture of the real shipyard that we're going to use. And then once it's built in a year, we barge it to the site. And then on the right, it's a real candidate site. It's a picture of the real candidate site. So we're going to either ballast or tether the power plant to the seabed. And when we're done with the power generation after 50, 60 years, we're going to barge them away from the site and return the site to its original states. So where's the site? It's on the north tip of the Java Sea, as you can see on the map here. It's in a low tsunami risk area, low seismic event risk area. So the Indonesian state electricity company is conducting the site study at this moment, and we expect to get more information from the site early next year. So that's the construction, but how do we convince the regulators that we can actually safely build and operate the power plants? So our approach is to test everything, and we test it and we know it's going to work. We're going to build a full-scale pre-fission test facility. We can test everything except for the chain reaction. We're using intrusive instruments, and we're going to do some destructive tests. And then we'll also be able to accumulate operating and maintenance experience when we have those massive testing facilities. So imagine or assume that we build the power plants, build the fleet, and where can we get the navigators and deckhands? So how do we gonna operate it? Deploying over 100 traditional nuclear power plants requires monumental efforts in training workforce. And in the old nuclear countries, you already get the force from nuclear navy, people who had experience in nuclear submarines or other type of nuclear facilities. But what happened to the new countries who had no exposure to nuclear in the past? Where can SORCON get the sailors for its fleet? Well, we took a slightly different approach from the traditional nuclear. So in the SORCON power plant, when the accident happened, the power plant will automatically enter a safe state and remain to be safe for half a year without any external support. So the operators do not have to take any action to direct the reactor to a safe state. Indeed, the operators cannot do anything to deviate the reactor from a safe state. So the operator training will be significantly simplified, and the efforts to train those sailors will not be as much as people would expect in the traditional nuclear. So let me just use another slide to elaborate this point. So I'm going to use the aviation industry as an example. So there are two major airplane manufacturers. Airbus, they put the autopilot and hard limitation at the center of their airplane. That means the machine always override human. While Boeing place the pilots at the center of the airplane, their pilot always override the machine. They have this privileges. And in SORCON, we choose the Airbus approach. So our operation is highly automated. The human operators have much less responsibilities comparing to traditional nuclear power plants. And our safety systems will always override human actions to ensure safety. We believe this is the best approach when we try to deploy a massive nuclear power plants in a country who had no exposure to nuclear in the past and who do not have seasoned pilots and our Sorghum plants do not have them. Well, in summary,
there's 1 minute left. Is it possible? Okay.
Yeah. Okay. So in summary, we have developed a molten salt reactor technology that can provide the world with low-cost dispatchable power that is clean and safe. And our technology perfectly addresses issues that currently hinder nuclear energy, which is construction, licensing, and workforce development. And our partner, Indonesia, has ambition for cleaner, more prosperous future. We can help. Thank you very much. For further information, you can visit our website.
Thank you, Koen, for the nice presentation and keeping time, 15 minutes. Thanks a lot. I would like to ask the participants, the students, please put your questions in the chat so that we can collect them afterwards, maybe also group them a little bit in topics, and then we will put a question to the panelists. And for now, I would like to continue with David Lang. David, can you share the screen? Is that feasible for you?
Yeah, yes, just 1 second. I think it was giving me a request about the recording.
Yeah, super. Yeah.
Give me 1 second. I'm not sure if I'm being blocked by a security feature here. So which is the share screen again?
You should be having
Sandra or Stefano,
yes.
do you know where the button is? Share the screen. It's, I think, with me, it's in the top right menu.
There is a menu called sharing. It's one of the menus that should be able to see in the window of the platform. There is sharing. You can choose which screen to share.
My apologies. It appears my security software is not allowing this. Deborah or Sandra, would you have the slides? Perhaps if you could just advance.
No, it's Yan Lin, the person who has the slide, not me, actually. Okay. Yan Lin, you do have the slide, correct? Yan Lin? I cannot hear what you're saying, but I assume you have the slide, so I'm making you now presenter so that you can share the slide for David.
Do I have? Yeah, I'm trying to work on the phones. Yes. I can run presenter. Yeah. I made presenter now, David. Can you see?
Yes, you are.
Something happening in the menu or not?
Yan Lin, we saw your desktop previously, so you were already sharing the screen and then you unshared it. So you have to share it again.
Okay. But I think, David, you are now presenter because you are out of my list. So I just made you presenter. David, otherwise you can send the presentation to me and then we can continue now first with the number 3 of the panelists.
Yeah, we can change the order. I did send the presentation about a half or an hour ago.
Okay. Then let me see. Truls can be. Truls has disappeared. Then I would like to ask Ian to present, if possible. Ian. Oh, Truls is there again. Sorry. Then we can keep order. Truls, can you? Yes, we can hear you. And
perfect. Can you also see me?
we can see you and we can hear you, and we see your presentation.
That's
Yes,
a good place to start.
Yeah.
So yeah, I'm Troels Schönfeldt, as it was said. I'm the CEO and also a co-founder here at Seabook. And if you Google us, you can probably find a lot of business pitches out there where I business pitch. So I will keep the business pitch short and talk a little bit about technical stuff, because I thought you would find that more interesting. So just a little bit about us. We are a privately held and privately funded company. That's quite important, because that means that we are aiming for a market and for commercialization. So we have almost no funding from government sources. We are actually every day we get more people in. So now we are, I think, more like 80 people employed, and then we have a few handfuls of students and interns here too, and some external people coming and going. And we are scaling towards 90 people by the end of the year, and hiring will continue into next year. So we are growing quite fast. We have our headquarters here in Copenhagen. Actually, the building you see in the background there, we just took over that entire building. So now we have 5 floors and 10,000 square meters, I believe. So we are taking over the entire building. And even though we are in Denmark, actually we're only around 25% Danes. So we are a very international team. And we also have business offices in both South Korea and in Singapore, with people working there. And then we have strong partnerships in the shipyards and heavy industries for turbine manufacturing and barge manufacturing and these things. So what we are designing is a almost classical molten salt reactor thermal design. We use a new moderator, meaning we can make it very compact, the reactor design, as graphite makes the core very big. And that means we are a good fit for deployment via power barges, similar to Turkan's plan. And barges are, as was already mentioned, very modular, so that's quite smart. The philosophy behind us is that since I was small, the politician has been talking, but we still haven't started to decarbonize. So the theory is that we will only decarbonize if we can find solutions that are cheap. And because of the urgency, we also need them to scale very, very fast. And this is the reason behind the maritime and shipyard deployment. I think a key point, which is not mentioned a lot, is actually the salt. If you can see my camera, I have a piece of fluoride salt here. It's the chloride salts are like salts, but the fluoride salts, they're like rocks because they have low solubility in water. And that's actually a very big safety barrier in itself, because it means that during extreme accidents, the radioactive isotopes are contained by the salt, so you don't need a lot of safety systems, or you have reduced requirements for them and have a much better safety profile. I sometimes say that instead of reducing the likelihood of an accident, we reduce the consequence of an accident. Our design has some really beautiful points to it. Cannot melt down or explode. It cannot release radioactive isotopes to air or water. Cannot be used for nuclear weapons. And then it can operate for 12 years without refueling, which is a big thing when you want to go to developing countries. We designed the barge like this. We have 2 reactors in front and 2 empty cavities in the back. We can then operate a turbine for 12 years. We can install 2 new reactors, ramp them up, ramp the old ones down, and continue operation up to 24 years in this kind of design. Also, this is something which, when you're not in academics, when you are getting into the industry, supply chains become very, very important. And this is, of course, a very simplified view, but we plan to buy components from North Europe. So we won't manufacture, they will be manufactured and delivered at a small plant here, where we can assemble the reactor itself and then ship that onwards to the manufacturer of turbines and barges. The barges can then be tucked to the grid and plugged in. And of course, with high temperature nuclear, you are very suited for not only electricity, but also for industrial needs. For example, hydrogen production, but also other things. So Brief plan, we want to develop this technology here in Denmark. We want to build it in South Korea, and then we want to power the world. And power is both electricity and heat, so everything. And when we look at the size of the supply chains, and when we look at the size of the market, it's not unrealistic that we should be able to, from those points alone, to ramp up to 200 power barges every year by 2035. And just to get your head around that, we have 450 reactors on this planet today. 200 power barges with 2, 4, 6, or 8 reactors on each means that we would more than double the number of nuclear power plants on this planet in 1 year. But that is nevertheless the need out there for new energy, green energy. And then I promised a little bit of technical. I won't go too much in detail, but I think there's something here that you might like. Our key innovation in Seaborg centers around the moderator. So a lot of our development efforts also centers around the moderator. And we are using sodium hydroxide as a moderator. And I usually say that the biggest upside in using sodium hydroxide is that it's not graphite. So you avoid all the challenges of graphite. But then on the other hand, it is sodium hydroxide, which gives you a whole palette of new challenges. So there are plenty of challenges. It's just different challenges than what it is with graphite. And then it also enables this compact design. So we recently expanded our lab facilities. We're actually in the building where I'm now. We are building another lab of 160 square meters these days. But the lab you see here is new. That's already finished, and we have people working there with a lot of new equipment, and it's very nice. You see the glove boxes there. They are actually to protect the fluorides from the people outside, not to protect the people from the fluorides, because fluorides needs very controlled atmospheres when operated. And on the left side, you see glove boxes that are used, or fume hoods that are used to handle sodium hydroxide. Here is another lab we just finished, which is meant for radioactive isotopes and thermophysical properties. So here we can actually handle some of the radioactive salts that we need to handle. We also, on the thermophysical property, we actually have academic collaboration too. So we're sending one to JRC soon to do measurements on our salts. Corrosion control is a very important topic when it comes to fluoride salt. I've added some pictures here, assorted pictures. But with the labs, we have managed to prove that that we have like the basic corrosion under control. The challenge now is to prove that that also works under flow and in an industrial setting. But on a lab scale, we can actually form the right protective layers on the materials, so they could, in theory, withstand indefinitely. Then to test in more industrial settings, here is an example of a loop. And I think this is a good example because it also shows the speed we have here. It's not there, the timeline, but this loop was built in a week. The next week it was tested for 300 hours. And 3 weeks later, it was dismantled and chopped up. And so it was only in existence for around a month with 300 hours of testing behind it. So we have a quite fast iteration cycle, and is concentrating on always trying to standardize where we can, so we can have really fast iterations on these kind of development efforts. Actually, by the way, that loop there, that's in a third lab we have. So we have a lot of lab capacity, but that's also important with molten salt reactors. Molten salt reactors are a chemistry reactor, not a physics reactor. But anyway, we still do physics. I'm a physicist myself, so that's my background, and so are the rest of the founders. We have a lot of different challenges with doing physics, but out here I want to mainly put your eyes on the figure at the lower end to the right here, which is actually measurements, real measurements of the scattering kernels of some of the salts in use, and I haven't seen that kind of data anywhere else. So that's quite new, and we did that in UK. That's pretty, I think that's very impressive that we have been able to do so. So we also have hands-on even in the analysis department. The analysis department, by the way, is doing a lot of analysis. We develop our own softwares. There's a lot of software that can simulate molten salt reactors coming from universities, but that software is typically not approved for regulatory processes. So you have to design in other quality, around other quality parameters to be able to use it in regulatory processes. And that's something we're quite focused at. Of course, engineering is engineering. Engineers love safety, and in the nuclear industry, everybody loves safety, so that's a good fit. There's a lot of development. There's a lot of things going on with external developers where there's guidance and assistance. And of course, engineering should guide your design progress forward towards having blueprints so you can build. And that's a big difference between universities and the real world, is that the real world is driven by engineers and supported by scientists, where the universities are just scientists. So that's a very, very massive thing. And we have a lot of engineering going on. I'll just bring up this, which is, I think, the biggest achievement we have produced so far. We've actually approached the regulatory system in a novel way. Instead of approaching through the nuclear regulatory authorities, you can actually live up to the same rules, guidelines, and standards by approaching via the maritime pathway. And the maritime pathway, as you might know, have, for example, approved nuclear icebreakers and a lot of nuclear military vessels. So it's not new to them, and they actually have the guidelines established. So we have gone into this process, and that turns out to be a much faster process than the nuclear regulatory process. And I believe we are the first one to get a phase 1 commercial approval of an advanced reactor with this one. And we are currently in phase 2, which will actually clear us for construction. And we believe we can achieve that already in 2023. So things are moving quite fast. If we can achieve that in 2023, we can actually have the first reactor built in by 2026 and in operation, delivering electricity to the grid. So that's a pretty big milestone, and all eyes on targets. That's where we want to get. That was everything. I hope that gives some more time for Ian. It's good. He's a clever man.
Thanks a lot. Thanks a lot, Truls, also for keeping time. Actually, we were a little bit late due to the delay with David's presentation, so that we catched up with the time schedule. I would now like to continue then with David, because I have his presentation here ready. And then David, just shout next slide, and then I will try to continue. Let me see, it should be. Can you see the screen now or not?
Yes, but it's not yet in presentation mode.
Oh, that's the, okay. I didn't know that. Yeah. Please, David, go ahead.
There we go. Yeah, next slide. Yeah, apologies. My added security here kind of blocking me. I'll try to go quicker and take less then, because I've slowed us down a bit. I'm going to focus on a couple things, mainly about our R&D program, a bit about the Darlington new build project, a little bit of an update on waste management. So next slide, please. So I won't go too much into our technology, but and most of you probably have a general idea, but just a very quick description. They are graphite moderated MSR converter design. Sometimes we use the word burner. Converter is the more technical term. So using graphite, a great moderator with challenges, of course, but we're dealing with those. Allows us a very low enrichment for startup. It's around 2%. And we stick to standard assay LEU. That's very important. Much of the world is not licensed, or there isn't commercial supplies above 5%. So we're one of the few Gen 4 reactors that can allow use of standard assay LEU. That's our makeup salt. We integrate our primary systems into a sealed reactor vessel, and this has a limited lifetime, as I believe you're seeing from some of the others as well. 7-year core unit lifetime. Or a seal and swap approach to this graphite lifetime issue, but it also gives you all the benefits of any metals of construction touching fuel salt only have that limited lifetime as well. Planned at about 440 megawatt thermal, giving us approximately 200 megawatts electrical. We're using an alternate carrier salt that avoids lithium or beryllium use for very low tritium, and of course enriched lithium to the level needed is not available in the world today. As well, a new approach to off-gas. We're looking at passive decay removal in situ without employing dump tanks. Safety is at the forefront, but that leads to cost innovation. So next slide. So again, I won't get too much into technology, but just a schematic view here. We have a graphite core. You can think of it as a pool type reactor in a can. Heat exchangers above, the molten fuel salt flows down downcomers. That allows us to have the reactor vessel wall at our minimum salt temperature. Salt flows up through the graphite and continues again through the heat exchangers. So that radioactive salt stays in that core unit for the 7-year lifetime. Makeup salt is trickled in, so there's a slight increase in the level within the reactor. But what takes the heat out is a clean secondary fluoride salt. But we also wish to employ a third or tertiary loop that will use nitrate salts, and those nitrate salts are very good in dealing with heat exchangers for power generation, for steam generator, for generating steam. They're very low cost salts, so that really helps in the ability to have thermal storage and balancing grids, etc. And roughly 600 degrees is an ideal for many high temperature heat processes. But let's move on. The next slide, sourcing our testing program. Yeah, next slide, Jan.
Yeah, something happened, David, because suddenly my screen was, oh, here it is again.
Okay,
So this is the next slide. Please go ahead.
Yeah, so, there we go. Okay. I think the simple thing to say is Terrestrial Energy has built a full nuclear engineering capability within, we're maybe unique. We're trying to operate as much as possible within the system. That can make things slow and can be not the exciting route, but it's the route we've chosen. So we have built in a programmatic fashion an extensive validation and verification test plan out to over 200 tests, and that will grow in the future in numerous areas: materials evaluation, reactor physics, thermal hydraulics, instrumentation, rad waste management, etc. We have deemed it the pragmatic and expedient route while operating within the regulatory system to rely largely upon sourcing of major R&D testing requirements to existing laboratories. These labs with the depth of experience for the quality of work necessary for the regulatory process. So it's a slower route. We've been at this for many years now and really starting to see the payoff. All laboratory suppliers undergo rigorous qualification process, and work is overseen by TEI R&D quality assurance staff. While some groups' labs have not passed this qualification stage, we have work either completed or ongoing with numerous institutions worldwide: Canadian Nuclear Laboratories, JRC in Karlsruhe, Energy Petten, Argonne, Idaho Oak Ridge National Labs, Angers Laborelec, and some of the universities, not inclusive, McMaster's University, Ontario Tech, and Virginia Tech. So next slide. So while salt property testing is nearing completion and really in the ultimate secondary verification stages, and we are continuing irradiation of 192 different graphite specimens, not 192 different graphites, but major commercial brands that will are potential for our system being studied in the Petten reactor. Most of our major focus now is on design and construction of reactor physics, thermal, hydraulic, and material testing facilities. Reactor physics is working towards both a hot subcritical pile, so temperature controlled, very likely at the McMaster's University, fed neutrons either from their operational reactor, or they also have an accelerator, and a similar fuel plus graphite assembly for testing within the Z2. It's a zero power reactor at the Chalk River facilities, or possibly the LR0 facilities in the Czech Republic. Thermal hydraulic work, such as heat transfer coefficient studies within tube, within shell, etc., and work on natural circulation for cooling are designed by numerous teams within North America, as well as a major dynamic corrosion test loop being designed by a team led by Angers Laborelec in Belgium. So next slide. So just a quick highlight on this facility that's being designed. It's by a team, John Cockrell, Angie Le Borelec, and CRM within France. The location of the actual test is not yet determined. It could be in North America or Europe. But that will be a large facility that will have pumped fuel salt, graphite specimens, tubing to allow us a whole range. And of course, we have many other experiments around the world. But I'll try to go quick here. So next slide. A little bit about the Darlington New Build project. OPG, Ontario Power Generation, is truly the only major North American or European utility forging ahead with plans to build SMR on its own existing sites. They're aiming for an operational unit in the 2028-2029 timeframe. There has been a previous full environmental assessment on the site for new build near the turn of the millennium that will greatly aid the process. Since October 2020, Terrestrial Energy's IMSR has been shortlisted to 3 candidates along with X-Energy's gas-cooled, triso-fueled XE100 and GE Hitachi's BWRX, their 300 megawatt smaller boiling water reactor. Decision is expected in the coming months. Hard to tell when it will be publicized. We've integrated, we're working and being paid by OPG because we have to do a lot of site-specific work. We've integrated their deliverables with our vendor design phase 2 work with the Canadian Nuclear Regulatory Commission. We're currently finalizing the delivery of our PSAR, Preliminary Safety Analysis Report. We have also upgraded, we're looking at a twin unit for the Darlington facility. They wanted a bit more power output, so that would be 390 megawatts electrical. So next slide. This is an actual photo of the Darlington facility outside of Toronto, Ontario. So there's existing 4 large CANDU reactors, and circled in red is the area that they wish to employ SMR. Next slide, please. And this is from one of our engineering partners, a representation. I know a picture is just a picture. I would comment that many engineers look at this, oh, you have square buildings, that means you're actually doing engineering, as opposed to some of the more elaborate shapes and sizes sometimes are shown. But that just shows within the plant parameters what we're looking at for twin unit. So next slide. A little bit on waste management. We have by and large tried to take the most pragmatic, simple approach to design, to R&D, to licensing. We do feel converter reactors have great flexibility for advanced fuel cycles, eliminating our own transuranics, perhaps those of other systems. But we really have viewed the pragmatic approach is a once through fuel cycle. And I'll be honest, the more I learn, I'm always very excited about recycling PU, et cetera. But the more I learn, keeping things, when you try to concentrate waste, sometimes you're introducing new waste streams, et cetera. We just feel, at least for now, pragmatic is once through. So our goal within the Canadian system, Canada is where we hope to have our first reactor. We have activities in the UK and the United States as well, but our first plant should be in Canada. So we're trying to fit in within the current strategy of the Nuclear Waste Management Organization, which has largely been set up to deal with CANDU waste. We feel it's the pragmatic approach is working with Synrock technology. This is a ceramic glass hybrid technology developed largely and owned by the Australians at Anstone. We have contracted them for feasibility study to assure that fluoride salts can, they have done this, they have worked on this for numerous waste forms, and they're currently near operation for Moly-99 waste at the Opal reactor, but it's just an excellent way to offer great durability of your final waste form. So we're really trying to go above and beyond what the current industry has within Canada. That is can-do bundles that would be placed in what's called a used fuel container, or UFC. So this is already designed, planned, etc. We want to fit into their waste. The SynRec technology involves hipping, high pressure, hot isostatic pressing or hipping into steel cans. So these fit very nicely within the can-do NWMO approach. The work we've done to date is showing that even though we somewhat dilute the used fuel, we have a lot of fuel salt. We have a fairly inexpensive fuel salt. We're still coming out at much less UFCs on an equal energy basis compared to can-do. And at the same time, for numerous reasons, significantly reduced heat load and external dose rates per UFC have been calculated. So that can really aid in the handling, potential loading factors within a deep geological repository. So that, I believe, was my last slide, and I'll kind of wrap it up there and look forward to questions later.
Thank you very much, David. I will unshare. So, yeah, we will keep the questions for after 15 minutes. And then we first go to Ian with the presentation that I think you can share yourself, Ian. Is that working with you?
Not yet. Yes, it's come up now.
Okay. Super. Yeah, I can see it, so I guess all other people as well. Can you put it in presentation mode? Then it should be
Will indeed.
clearly visible to everybody. Yes.
Is that working?
Okay. Thank you. Yes, that's working. Thank you. Please go ahead.
Thanks very much, everybody. I'm going to start with an apology. If I start coughing during this presentation, it's because I'm just recovering from a COVID infection. So please bear with me. I'm not infectious over a microphone. Okay, stable salt reactors. Maltex has a very clear mission. It's interesting how cost has come at the bottom of many groups' list of important things for nuclear. For us, it's absolutely at the top. Maltex was set up from a belief that unless we can get nuclear energy down to the point where it is cheaper than fossil fuels, then we will not solve the climate change problem. And it's really is as simple as that. I'm not going to say much about the company structure. Maltex Energy is actually two companies. Maltex Energy Canada is where we're pioneering our fast spectrum version of the stable salt reactor called Waste Burner. New Brunswick Power is our customer. They have the intention to deploy a advanced reactor on their site in New Brunswick. We've completed the first stage of the vendor design review in Canada. We've had very generous funding from the Canadian government, and we feel extremely welcome in Canada. It's a great country in which to do advanced nuclear, as I think David can attest. In parallel with that, Maltex Energy UK is pioneering the development of our thermal spectrum reactor, low-enriched uranium, which I'm going to say very, very little about, as well as actually providing a large amount of technical support to our company in Canada. Okay, we start in Maltex from a really very fundamental position on nuclear safety. This triangle you see here is something which is used globally as the guide to how you achieve safety. And it's an inverse pyramid. The most effective and usually the cheapest way to achieve safety is to eliminate hazards. If you can't eliminate them, then substitute them with a lesser hazard. And only then go down to engineering controls, admin controls. The interesting in nuclear is that after the Chernobyl disaster and the 3 Mile Island very near disaster, all the effort in nuclear went into improving the engineering controls and the admin controls. And that, frankly, was a mistake. At that point, we should have looked at the fundamental hazards and said, how do we get rid of those hazards? And that is what Maltex has at the heart of its philosophy. And that brings us to multi-salt reactors for reasons which I won't go into because I think everybody on this webinar will appreciate that. What we're doing differs really very fundamentally from what I think every other company in the molten salt reactor field is doing. Almost all molten salt reactors, all ones we've heard about today, I would call them children of the Oak Ridge National Lab molten salt reactor experiment, which was a fantastic experiment. And the core of that technology is that you have a molten salt fuel. It goes through a reaction chamber where it undergoes fission, gets hot, goes critical, and it then moves through a heat exchanger to take the heat away. Well, the consequence of that is you have to move your extremely radioactive fuel salt around what is essentially a plumbing system, pumps, valves, flanges, you name it. Our approach is fundamentally different to that. We take the molten salt fuel and we put it into fuel assemblies which are really very similar to the fuel assemblies used in current reactors. It sounds like an extremely obvious and simple thing to do. It actually isn't. It's a new concept, and the patent on that process, very broad patent, is now granted worldwide. So that is the fundamental difference. Moving on to the SSRW, our waste burner reactor. I've just summarized here some of the ways that we've applied our approach of eliminating hazard to achieving safety. It's not all of them, but it's a good selection. We've got a strong negative temperature reactivity coefficient, as most molten salt reactors are able to achieve. But that's really incredibly important. You have an intrinsic stability against overpower transients. Our fuel tubes, the one way they really differ from conventional fuel tubes is they are vented. That prevents the tubes being pressurized, which reduces very, very substantially, probably to zero, the probability of a fuel tube failure. The reason that we can get away with venting the fuel tubes is that with molten salts, the highly radioactive fission products are basically non-volatile. What gets vented is essentially noble gases. We have a decay heat removal system which is passive, always on. I think that's probably true of every reactor we've heard about this afternoon. It's essentially a requirement in any modern advanced reactor. You know, anybody who designs a reactor which actually requires an active heat removal system to keep it safe has done something very, very wrong. They may as well build a PWR, frankly. And finally, we have a principle. We achieve continuous refueling in this reactor, not by topping up with additional enriched uranium in the way that conventional molten salt reactors do it, but by replacing fuel assemblies while at power. This is a really quite important factor in achieving safety, because what it means is the core can never have a significant amount of excess reactivity. And that removes a whole tranche of ways that the reactor can go wrong in a dangerous way. That applies to many molten salt reactors, and it's an extraordinarily important intrinsic safety factor. Okay, a quick comparison of the stable salt reactors versus conventional molten salt reactors. The big one, the one that actually led me to conceive of this reactor, was avoiding pumping this extremely radioactive material around a complex system. If you have a pump system, you have to do the safety analysis for how you cope with leaks. And that's perfectly possible, but relatively complex. And I believe will become quite expensive. The second one I've got here is materials challenges. Molten salts, people say, are highly corrosive. They're actually not. That's not actually true. Molten salts handled properly are actually not particularly corrosive. But it does mean you have to get the chemistry right. We have a system, a patented system for achieving no corrosion in our fuel salt, of simply putting some zirconium metal into the fuel salt. It works beautifully. It makes the molten salt strongly reducing. It essentially eliminates corrosion. That simple technique can't be used in the pumped salt reactor because the zirconium does migrate. Whereas we don't really care if it moves from one place in our fuel tube to another. If it's having a pumped salt reactor, it will end up wherever it'll do the most damage. It's a law of engineering. So the stable salt reactor allows corrosion control in a really very simple way. The third one here is something which is somewhat less obvious. When you look at nuclear safeguards, this is the anti-proliferation rules which the IAEA enforces. There are really two different regimes of safeguards. The first applies to bulk fissile materials, such as you have in a nuclear reprocessing plant. This requires you to measure the quantity, the volume, and the composition of your fuel multiple times. When you're looking at conventional nuclear reactors with solid fuel, safeguards treat the fuel as items. So you know how much plutonium you put into the fuel assembly when it was built, and you track that fuel assembly just by its barcode, effectively, throughout its life from cradle to grave. That's a relatively simple safeguards procedure. I say relatively, no safeguards procedures are actually straightforward, but it is a relatively straightforward process. Because we put our molten salt fuel into tubes in this way, we get treated as items, which simplifies the safeguards within the reactor really quite significantly. And now in the interest of balance, the downside of SSR is a very fundamental one, which is that we've got a lot of metal in our reactor core. That makes our neutronic efficiency lower than a pumped molten salt reactor. And that's significant if you want to be a breeder reactor, for example, very significant if you want to be a breeder reactor, but doesn't actually affect the economics. As I said at the beginning, for us, this is all about the economics. So I'm going to talk about economics of nuclear a little bit because it's of general importance, I think, both to the nuclear sector and to the world. This is how I put it, mostly to annoy the older nuclear industry. Nuclear industry is dying out there. If you look at the projections for the number of PWR reactors on the planet, they're in decline, notwithstanding all the new build going on. Two things are driving that. The first is no news to anybody. They're getting too expensive. There's been a massive increase in capital cost, which just challenges the basic economics. And there was a lovely study done by the Electric Power Research Institute in the USA, where they looked at how in the USA, nuclear energy would penetrate the overall market at different capital price points. The look was really very simple, very clear. At $3,000 per kilowatt, you have a business, not a very big one, but it's a viable business. At $2,000 per kilowatt, you're the dominant technology in electricity generation. That's where you actually want to be, the $2,000 per kilowatt. Pressurized water reactors are running $7,000 to $8,000 per kilowatt and going up all the time. So they're really not terribly relevant. The second factor, however, is a bit less obvious. People talk a lot about how we need baseload generation. Well, no, we don't, not anymore. In any electricity system that has significant levels of renewables, there are times that those renewables provide all the power you need. And there is no market left for a baseload generator. This has huge and increasing consequences. This is slide shows real data from the UK for last year. If I'd done it this year, it would have looked a lot worse. What you're seeing is that there are significant periods of times when electricity wholesale prices fall down to negative levels. This week in May last year, wholesale power prices reached minus £52 per megawatt hour. Minus. That means if you were producing electricity at that time, you paid the grid operator £52 for every megawatt hour you produced. Now, who on earth would do that? Well, there are two electricity generators who do that. The first is renewables, who have a guaranteed price. So they don't mind if they have to pay £52 to get rid of electricity because they're going to get £60 back from the government. Highly subsidized. But they keep on generating and making money. And then you have nuclear. Nuclear actually pay those negative prices. Actually pay them. And the reason they pay them is it costs too much to turn their reactors off for that period of time. And so they just absorb it. But in terms of a business model, that graph is a nightmare. So, in order to make nuclear work, we really need to achieve carbon-free nuclear energy whose capital and fixed costs are low enough that, sorry, missed a slide, that they can be profitable when they're operating at 30 to 50% capacity in competition with fossil fuels. That is very difficult target to achieve. It's not about levelized cost of electricity, because sometimes if you're using Bristol power, you will pay money to get rid of electricity. Okay, so what's our solution? This is not unique to Mortex. A lot of people are looking at this now and they're right to do so. The solution was found essentially by the solar energy industry, who found you can store high temperature heat in tanks of molten salt very efficiently for quite long periods of time. And that's the way that we at Mortex intend to deploy the reactors. We would have in our base load business case a 500 megawatt reactor which tries a 1,500 megawatt power plant for, on average, 8 hours a day. That can be flexed depending on market. And the fundamental technology that allows that to happen is we call grid reserve. It is thermal energy storage. It's very, very cheap. Which brings me to my final slide, which is about cost per kilowatt of nuclear energy. The dark blue bars on this are real data from the USA of how electricity, about the capital cost of nuclear has simply risen up and up and up and up over the whole time. And I just lost my slide. I hope that came back. What this shows is the impact for the SSRW of first doing safety right, which is getting rid of the hazard rather than doing fancy engineering to control it. That brings the capital costs down well into that blue area on the graph where nuclear is both viable and dominant. And when we combine that with grid reserves, so we have the ability to deliver peak power rather than baseload power, the cost per kilowatt goes down even lower, down to around about $1,000 per kilowatt. That is a real business case, and that is what we are pursuing. At that point, I'll just say thank you very much.
Thank you, Ian, for this nice presentation. Maybe you can unshare, and then we can have a look in the... Maybe I have to unshare you.
If you do that, that would be great. I can't find out how to unshare. Thank you.
So this is done. So welcome to the panel discussion. Stefano and Sandra, questions from the audience. I have a few ones here. And one question is very simple.
Jan-Lin, I do have problems in hearing you. I don't know if it's actually a connection problem or what.
Somebody who asks if the slides can be shared. Well, I hope. We can go.
Jan-Lin, your audio is very different, I think, for everyone.
After if you wish, you can.
And then maybe you can
share.
Stop your video. We don't hear you.
Maybe we should just mute him and do it ourselves.
Yes.
Assorted sounds.
Jan-Lin, can you hear us when we are talking? Okay, because we are having issues in hearing you actually. So, okay, can you just try again? Probably without the video is better. Not that much.
Because you cannot hear me. You
Yeah, it's still only occasionally coming through. I would suggest sometimes just call in by phone. You should at least be able to get the audio. And maybe in the meantime, Sandra, would you have some questions you could start with, or?
Sure. Well, I will start picking the question from the audience. There were, on top of course, of the congratulations that all the speakers received from the audience regarding the interesting presentation that were given. There is a generic question. I may start from one that is to explicitly proposed to all presenters regarding to what extent have you... Yes, Jan-Lin. Jan?
What extent?
I'm just reading, Jan-Lin, I'm reading the question for the panelists.
Can you hear me?
Jan-Lin, you're still breaking up. We only hear every now and then.
Okay, I was reading the question. To what extent have you considered international safeguards implementation in your design?
Oh, that's strange. Stop my video. That's me. Is there a... I can hear you. Yes, now. Okay, can you maybe
it's really
it's a little bit hard.
It's becoming complicated, let's say. Jan-Lin, okay, Jan-Lin was muting, so I'm trying to cover, let's say, while probably Jan-Lin is trying to fix the issue with the connection. So I don't know.
I'm now unmuted, I think.
Yes, you are.
And can you hear me now, or is it still?
Yes, we can hear you very well now.
Oh, okay. So there was a question about the regulator, and I don't know if some of the panelists can actually answer this question. Can you repeat the question, Sandra?
Sure. To what extent have you considered international safeguards implementation in your design?
Yeah. Is there somebody who wants to start answering? Truls, can you? Yeah.
Yeah, I can start. There are several sets of rules that you have to be in compliance with when deploying nuclear, and the non-proliferation safeguards are quite fundamental. It's in many ways the founding document of UN, and in fact the European Union is also founded upon that document. So it's quite important that you don't change those rules very much. So basically you have one option, that is be in compliance. That's it. So you have to, no matter how you design your reactor, you have to be in compliance, and it's something you have to think into every aspect of your undertaking, going to the supply chain, transporting fuel, getting into operation, how you operate it, how you build it, even in the development process, before you even have access to your uranium, you need to be in compliance with the safeguards.
Is it different is there some special route in Canada? Because many startups are actually connected in some way to Canada. And maybe David or Ian, can you comment on this?
I'd happy to comment on that. So I think it's worth starting by just explaining the position of the IEA on safeguards. The IEA assumes that both the operator of the reactor and the government of the country in which the reactor is operating are actively seeking to divert fissile material to make weapons. There is an assumption of bad faith in the IEA rules. That's entirely correct. It should be so. And so you have to design your plant in such a way that, with the active connivance of the local nuclear regulator and its government, you cannot divert fissile materials in sufficient quantities to make a nuclear bomb. That puts a really major constraint over this. One of the areas which is, I mentioned in my talk, is very relevant to molten salt reactors, is that they are, by their very nature, in case of pumped molten salt reactors, they are a large vessel of fissile material, which will sit there for many, many years with potentially material coming out, being reprocessed, and potentially new fissile materials being added. And you have to have confidence that in that whole system, no fissile material can be removed, even by a government-supported evil organization. That's a real challenge. It's the same challenge that is actually found in reprocessing plants, where you actually have large volumes of radioactive material, and you have to convince the IAEA that no diversion has taken place. It's a major challenge for molten salt reactors. It's one of the reasons why we actually went down the route, Moltex, of putting our molten salt fuel in assemblies. But I don't want to say we're free of it, because we are a plutonium burning reactor in Canada, which means we're handling plutonium in a non-nuclear weapon state. And so there's no get out of jail free clause as you are if you're the USA, for example. And so there's our major concerns there. And it is one of the big challenges in actually going to a genuinely new reactor technology like molten salt reactors.
Yep. Thanks a lot, Ian. Is there somebody else who wants to comment on this? Or I don't know. I cannot see the questions in the.
Okay, I can
chat.
proceed. There are Ian was already talking. I may redirect to him a question regarding the online refueling process. There was a request to elaborate on this aspect regarding the waste management strategy.
So it's quite useful to use light water reactors as the analogy here. So actually better to take advanced gas cooled reactors from the UK, which do online full power continuous refueling. What you have here is you're removing a fuel assembly which is strongly heat generating. Time it is quite strong enough to actually overheat itself. So you need an initial stage where that is allowed to cool. Now, conventionally, that's actually in a water reservoir. And that's not a very good idea with molten salts for pretty obvious reasons. So with the SSRW, the steel salt reactor waste burner, we lift the fuel assemblies from the core and we put them back in the same tank around the periphery of the core, outside the major neutron flux, to allow them to cool for around about a year, at which time they are then able to air cool. We take them out through an airlock into essentially something that looks very similar to a standard dry store flask. And there they can decay until you're ready to reprocess them. And because that reactor is a plutonium burner reactor, on reprocessing the fuel that comes from it.
Yep. I do believe that all the other concepts also have decay time before processing starts. Is that correct? Because or is it? Well, David is a little bit nodding.
Well, just depending on your meaning of processing, we do not plan any processing. It may be in the future, but for now, it's a once-through process.
Yep.
Yeah. So it's, at some point, it's conditioning of the waste for more stability and durability.
That's true. That's what you mentioned, indeed. And how is this for Seaborg and Thorcon? Do you have processing in mind, or?
For us, it's pretty simple. You have to comply to the safeguards, and these. While I come from neutronics myself. I love neutron economy, but that's not economy. You basically only have one choice, and that is to be in compliance. And to be in compliance, you have to choose conventional pathways. David went very well through that in his presentation. There are methods for handling waste, and you handle it via those methods. If you want to do it differently, diverge in any way. All you have to do is change the law, and you can't do that as a startup. So we just take the approach of once true, no fancy pantsy, no processing. We handle the waste as conventional waste.
Okay. So if I may, for Sorkang, we're not having a plan to reprocess the fuel immediately. It could be an option in the future, but definitely at this moment we don't have such a plan of doing it. We just, as David mentioned, we condition the fuel and making it ready for a long-term storage. And I do want to highlight that as long as we're using liquid molten salt as a fuel, regardless of the technology we're using, we're facing similar issues with the waste, regardless of what type of container we're using, as long as you're using salt. But I think there is a little, I mean, this issue is a bit exaggerated to a certain level regarding the nuclear waste. Because if you think about this, the whole nuclear waste that has been generated since the inception of nuclear energy, the whole waste can be fit into 3 to 4 football fields with 10-meter steps. So in terms of volume and mass, it's not a big quantity. And we certainly will be able to manage that.
Yeah, thank you. There is another interesting question in the chat, and it's about fast thermal spectra in your reactor designs, because there is one fast reactor design by Moltex in Canada, the MSFR that Elsa presented before the panel discussion is also a fast reactor. The other 3 have started with the thermal reactor design. Can you give some, some reasons why you evolved in this way, why you started with the thermal design? Is there a specific reason for it, or is it just the combination of factors?
Who are you asking again?
Yeah, maybe you started with the 4 of you, I would say. Truls, you first. Is it okay for you to start?
Yeah, I mean, our choice was made very early. Again, somewhat based on wrong assumptions, but also kind of luckily, I think. And things can change as you go along. But again, it comes down to compliance, right? You cannot diverge from the proliferation safeguards, and that means that you have to use low enriched uranium. You have to dismantle waste in normal pathways, and you have to use known materials. So that those 3 things basically means no thorium, no waste burners, and no fast reactors. And that's of course a truth with modifications. Fast reactors are actually possible especially in weapon-bearing countries, and you might be able to get an exception in, for example, Canada. And I think that's what Moltex is working on. And I will say from a neutron economy point of view, I really think fast reactors are most beautiful, and they give some big upsides over thermal reactors, but they also give some new challenges. So our choice was based on the fact that you have new challenges, and especially the regulatory challenges. I don't foresee us solving them. When they're solved, we might want to change to a fast reactor, but that's going to be 20 years from now.
David, do you do something to add to this, because you're doing a lot of radiations on graphite, so it's also
yeah, I largely agree with what Truls was bringing up. Those are very good points. It does boil down to pragmatic. There's a lot of exciting advantages of the fast spectrum, and I as well probably agree that in 50 years we probably will be majority of fast reactors, but we've just felt the more expedient route, the pragmatic route, has been the thermal spectrum for many of the reasons Truls mentioned, the ability to use standard assay, LEU, etc. We like graphite. It does have a lot of challenges, but also just a reminder, especially from the early program, that thermal inertia. We have a pretty large system for our power. We have a fair bit of graphite. We have a lot of fuel salt. That really slows things down when you get into any transient analysis. We value that as well. So, yeah, definite advantages of both directions, and I'm glad to see that both directions are being taken forward around the world.
Yes. Ian, Koen, would you like to add something, or?
I would absolutely support what's just been said. Okay. I think there's no better reactivity in fast and thermal. They do different things. Thermal reactors are really the only way you're going to get a reactor working with less than 5% enriched uranium. And there are very, very good reasons why that's necessary if you're going to do a widespread global rollout. So thermal reactors are an essential part of solving the climate change problem with nuclear. The reason we're doing fast reactors is not because they're neutronically efficient. Our reactor is horribly neutronically inefficient. It's nowhere near a breeder. But the world is building up large stockpiles of plutonium. And there's two views on that. One is that it's wonderful, we should hang on to them and go to a plutonium economy with breeder reactors at some point. And then there's a view that, do we really want large amounts of weapons usable material around the world? And to be honest, we take the second view there, that there's first of all a good business, and secondly something of a moral imperative to basically get rid of the plutonium waste from the first nuclear generation and the one that's coming up. That's actually the right thing to do for human society.
Yeah, and Elsa, I remember that in Europe, we also started with a thermal reactor with thorium fuel cycle. And can you explain maybe the reasons why we shifted to the fast reactor?
Yes, I hope I explained this during my presentation, so longly. Yeah. But
there's a few extra students in this session, so.
Yeah. So without slides, but when we consider neutronics and when neutronics behavior in for a breeder reactor in the thorium fuel cycle, and for example, the MSBR, and when you reevaluate the MSBR with the thermal fuel cycle, you can show that the feedback coefficients are not negative. It means that they are not good. In fact, due to the part of the graphite which has a longer feedback coefficient in time, but positive, which is not good. And also, when you consider breeding, due to very high capture rates in graphite in the thermal spectrum, you cannot have a breeder reactor. I think it's mainly this. Also, the graphite is much less irradiated than in thermal neutrons compared to fast neutrons, but you have a large amount of graphite. So the quantity of graphite to manage per year is very large when you consider graphite. I don't know for other kind of moderator, but regarding graphite, it's not positive. So it's why we suppress graphite finally. But I agree that when using only enriched uranium, you have a lower enrichment with the thermal spectrum. It's not what I call to use only enriched uranium, but to start NSR. And I think that we have to start NSR one day to prove that it's possible to operate them. Yes, maybe if you want a large deployment of small NSR based on enriched uranium, thermal version is better, probably. Yes.
It's a very interesting physics point. Yes, in the early program, it was just weakly negative, depending on how you design. That was solely due to thorium and uranium-233. U-233 and thorium does give you a positive graphite term, but in what many of us are proposing, when you're not using thorium and it's low enriched uranium, we actually have a very strong negative graphite term. So all our terms are negative at the start, and as plutonium builds up, that gets weaker, but we stay slightly positive in the graphite as well. So it's just a fundamental difference when you don't have the thorium and 233 there.
I confirm that we are looking at epithermal NSR right now in the frame of the NAREA startup, which is a French startup. developing a very small modular reactor for a large deployment. So I cannot add elements since it's confidential today, but I think that in the coming years, we'll have more data on this kind of reactor. And yes, the idea is to use plutonium and to have a large deployment and with very small units of reactors. So in this frame, epithermal may be better than thermal spectrum is maybe better, but we are working on this.
Yeah. You showed the taxonomy, Elsa, and from this you could see that there's really a wide variety of MSR designs possible, depending on the fuel cycle that you deploy, depending on the moderator or no moderator, or the kind of fuel processing, etc. you have. So there's really a large design space. That's maybe the big advantage of MSR, I would say.
And a lot of viable configurations. It's what I start by this. I think it's very important. If we find non-viable, we will not deepen them. But since they are viable, we have to see what they offer. I think.
I thought Koen also. Please go ahead, Koen.
Yeah, I just want to add one point on top of what Elsa just said. There are many advantages of using fast spectrum. When we started, our focus has been how can we build this part from as fast as possible, as many as possible. So we choose the technology, thermospectrum technology that has been tested, and it will soon be tested by others. You see there's test reactors being built in China. There's going to be a test reactor used by Kairos in the US. So you're going to see quite some thermal spectrum test reactors in the next few years. So we're going to just take advantage of those past experience to enable us to build as many as possible.
Yeah. Thank you. Maybe there's another question. Looking in the chat, I myself was wondering, hey, you all started some kind of business, and there might be students who think, well, yeah, how do you actually start a business in the nuclear field? Because if you want to build a nuclear reactor, you need certainly hundreds of employees and so many different disciplines that you need to tackle, etc. It's a huge work, I would say. So how did you actually start yourself? Is there a special trigger that you convince yourself that you would like to start a business, and how did you actually take off? Is there somebody who wants to start with answering this for the young people among us that also are thinking of starting a business, the students?
Go on, David. You're the one who started first. You should answer first.
Yes, you spend years and years traveling the world talking about this for no money. Then you finally find great business partners, and the world catches up. We are seeing an explosion, a true renaissance in the Gen 4 field. But yeah, in my case, it was kind of working on this when it wasn't a very popular item, so to speak, but found excellent business partners. We started the company, raised funds, and within Canada, CANDU reactors are still going, but they're not really a going concern. So we've really, it's finding the right people. So we've been able to build up from the ground level a nuclear engineering firm. We probably have a bit of a double peak. We have probably half our employees that are ex-CANDU and over 60, and then a lot right out of university. So yeah, it's finding the right people to work with and building it up from there.
Yep.
It's easy. If you're fusion, you can get money thrown at you left, right, and center, but it's harder in fission.
Yes. Ian, did you found next, or did I?
Oh, you go, Trolls.
Okay, well, I think the first thing you have to do is be insane. I mean, nobody in their right mind does it, and I had no idea what I was throwing myself into. For us, it was a combination of I think my co-founder Espen said it very well. He said, "How can I come home to my daughter and look her in the eyes and say that I didn't try?" But then when you try, it's a hard ride, right? You start by living a few years on the road, not having money for anything, and then suddenly you have 80 people employed. And when you have 80 people employed, you realize that you have moved people around the world to come to Denmark with their families and work here. And if you fuck up, they will also take a hit. So suddenly you have insane amount of responsibility. It takes a lot and it's not easy. But I'll also say for me, it's been the most crazy thing I've done and also the best thing, but also the hardest thing. And there are many weeks where even if you don't sleep, there's still not enough hours in the week. Any young person out there, if you have a good idea, start a business. And also, don't do it. It's a stupid idea.
Ian, something to add?
I'm not sure my personal experience is much of a guide to students on this this call. I retired from my first career when I was 50. My second career was building up a biotech company, which I did for 10 years, and then retired again. And then I got an idea. What actually the reason I came to nuclear was I read a newspaper article saying that EDF were going to be paid £95 per megawatt hour for power from Hinkley Point C in the UK. I thought that's utterly insane, which I still think is the case, by the way. And that just got me interested in the economics of nuclear, having not worked in nuclear at all through my career. Having identified why it was so expensive, it's the step there to say, okay, how can it be cheaper? I came up with an idea and I had a choice. I could either write a scientific paper and then nothing would happen, as most of you will know, or start a business. And so I already started a business once. I thought, I'll give it 10 years. And that was actually 10 years ago. But I think it's doing well enough now that I will probably carry on.
Now you survived the corona, so hopefully we can keep you another decade.
Yes.
Something to add by somebody? I also noticed from your CVs that a few of you already started the business before, so you must have a kind of entrepreneurial attitude, I guess. So you must, or are you just folks like anyone else? Is it nothing special to start a business?
No, Troll's got it right. We're all insane.
Okay. A little bit the insane inventor that wants to conquer the world.
I started with I have no prior experience in business, and I actually didn't know what a business was. I became the CEO because I showed up at a meeting too late when I was the CEO. And that was because we didn't know that a company needed a CEO. So suddenly we were contacted by the authorities, told that we needed a CEO, and then I was pointed out. So that's how it worked for me. It was a wild ride, but at the stage I am now, I know that I will never do anything else. So no matter how Seaborg ends out, I'll found another business.
And Lane, just to quickly add, one we're involved in boot camp sometime. One thing I like to add as well is I wouldn't say there isn't a need for more nuclear reactor vendors, but we don't have a shortage. But there's a lot of other entrepreneurial activities that within this field. If you have instrumentation ideas, pumps and valves and materials ideas, etc., there's a lot of room for innovation, entrepreneurship in those areas as well.
Yeah. So maybe that's a wise advice, that there's also on smaller subtopics a high need for new companies, etc. So that it doesn't sound big anymore. Maybe if you stay on your own expertise and you can start a business and support the other business developments in the nuclear field. I was also wondering myself that there in some of the designs that you presented, there is some overlap in the kind of design space, you would say. Some of you are using graphite, so I guess what one person is doing on graphite, maybe but what Truls did going to Rutherford to measure the thermal scatter kernel, if I'm correct, and what David did to irradiate graphite in the high flux reactor in Patton, and maybe in Thorcon there was also some activities in this field. Wouldn't it be much better that you, at least for these activities, try to combine research in this field, or is it too sensitive from the commercial point of view to work together? Maybe this is a tricky question, but I'm just wondering if you work together with other startup companies and if it could speed up development.
You can tell that.
No, it's very quiet, so the wrong question.
And I certainly wouldn't rule it out, but it is difficult. I know we hear this refrain, why don't we all just work on the same reactor? Well, business doesn't work that way. But yes, there's probably the ability, and we're probably guilty of not doing enough of it. But yeah, that's
I understand it.
Question, yeah.
There's another way we can collaborate. We can work through academics like you guys, SAMOSAFER, and if you offer a capability like chemistry or property measurement or some kind of a simulation, and if we work with you and basically you develop this technology, then we can all share. It's not shared between the companies, but through a project like SAMOSAFER.
Yeah, that was the next question I had in mind. How can academics work together with startups and maybe speed up the development?
Maybe I will just take that because we are very pro collaboration in CBOC, and we have some collaboration on certain areas with both industrial partners, and me and Ian have worked a lot together earlier. But so we have collaboration. I strongly encourage that we should have more. I think that, and no offense to the academics here, but I think that I see is that the academics are very busy finding irrelevant results and doing designs that are not, for example, the fact of going for a burner, for a breeder reactor instead of going for a realistic reactor is symptomatic of this effect. So it's quite hard. What we have done with success sometimes is through either PhD students or master students or even bachelor students had projects running where they come here and intern or something, and then we can publish the results afterwards. Of course, we cannot publish everything, but a lot is publishable, and that way we can get something which is relevant for us out there, and then it may or may not be relevant for others. So there are ways, but I think as a community we are definitely not good at it, and I've said this before. I see the molten salt reactor community as similar to the personal computer community in the early 70s, where nobody believed there would ever be personal computers. But what they did was collaborate, and it's not a winner takes it all market. I mean, if one of us here in this room succeed in deploying the first, I'm sure the rest will follow. There might be one falling here and there, but most will be winners, just not first prize. And the world needs a lot, so I strongly encourage more collaboration. But it's also very hard because there's a lot of strategy in it and IP and so on.
Yeah.